hyper-contractivity. So take it away now.
Okay, so I'll start with talking about hypercontractivity in general. So we have a function the Boolean cube. We call it as its Fourier expansion. Where the characters chi-s are an orthonormal basis given as the product of the elements in S. Okay. On the Boolean cube, we have a certain process called the noisy process. Okay. What this noisy process does is we take the Boolean cube and for each x, we're going to define a random walk of some that gives us some y in a small neighborhood of x, and then we are going to define an operator called the noise operator that's defined by averaging our function over this y that's close to x. So how is it given formally? So we're going to define y according to this distribution n epsilon x, where each yi, so there are two possibilities. Either we remembered xi, so with some probability epsilon, we remembered xi and then yi is xi. And with some probability, we forget it. And so after we forget it, we resample it uniformly out of -1, 1. That's too small. Okay, so that's our random walk. So we start with an x. Independently for each I. Yeah, independently for each I. Okay, so we start with some x in the Boolean cube, and then we get some y that's close to x by looking at all the coordinates of x. Each coordinate we remember it, and then we let yi be xi. And if we forget it, we choose it to be uniformly at random out of -1, 1. And eventually we get this y that's close to x. And then associated to this random walk, we have a smoothing operator. So we can define the noise operator. Given by taking the expectation. So its value on x, 0f of x, is the expectation over y chosen in the small neighborhood of f of y. And the hypercontractivity theorem that we're going to talk about, we can already state it. So we have the LP norm of the function. So if we have a function on real valued function, so not necessarily Boolean, its P norm is defined as the expectation of f to the p. And in probability spaces, we have, so in probability spaces, the P norm is at most the Q norm if P is smaller than Q. Okay, so why is that? Let's prove it in the case where P is equal to 2 and K is equal to 4. Yeah. So we want to upper bound the expectation of f squared by the expectation of f to the 4. So how are we going to do that? We can write this expectation of f squared as an inner product between f squared and the constant 1 function, and then apply Cauchy-Schwarz to say that this is at most form of f. Because the 2 norm of 1 is 1. So we get that the 2 norm is at most the 4 norm, and it's true in general that the p norm is smaller than the q norm when p is smaller than q. So we can imagine this picture that we have the L2 unit ball of all f such that the 2 norm of f is at most 1. The big L2 unit ball, and inside we have the L4 unit ball. And usually when we have an operator, we can talk about its contraction properties, that it sends the unit ball into itself. But the noise operator has these very strong hypercontraction properties, that it manages to squeeze the big ball into the small ball. So inside we have this T of 1 over root 3 of the LT ball. The picture, so let's state the theorem. So we have a function really a values function on the Boolean cube, and we have epsilon that's smaller than 1 over root q minus 1. Then we get that the t epsilon of f, the q norm of that, is at most the 2 norm of f. Smaller than q. Yeah, so if q, this is the picture for q equal to 4. So if we start with the function in the L2 ball, this t epsilon operator, it squeezes it into the unit L4 ball. Are there any questions so far? This is a hypercontraction.
Why is it a contraction?
Okay, why? So every operator that corresponds to random walk is a contraction. This follows from a Jensen inequality. I can prove that. Yeah, so we have, so let's say you're trying to compute, yes, so let's prove it for this operator. We have this operator of f of y, and then we are trying to take absolute value and take it to the 5th power and take expectation over x. So using Jensen, we can put the absolute value inside and say that this is at most the expectation over x and y of fy to the p. But then we can use the property that when we choose x randomly and y according to the noisy process, we get y that's distributed uniformly in the Boolean cube. So this is the norm of f to the p.
But this is true for every norm. You can also do it using the Penguin. Maybe it's the same.
I mean, yeah, the only thing that was important is that this random walk sends the uniform distribution into the uniform distribution. Otherwise, it works in every stationary random walk. Well. Okay. I figured it out. Okay. And it turns out that this noise operator is very relevant when we care about the decomposition of the Fourier spectrum of a function with respect to the degrees. So if we start with a function f, that's fact. If we have a function, then T epsilon of f is the sum of epsilon to the s times f at s times chi s. Give the proof because it's simple enough. So we have this operator T epsilon is a linear operator, so it's sufficient to show it for these characters chi s. And this T epsilon of chi s is the expectation, yes, put it x, it's the expectation over a noisy version of x of the product of I in S of yi. This is chi s of y. And now we can use the fact that these yi's are independent because we're doing everything independently in each coordinate. So this is the product over I in S over the expectation yi. But then yi is xi with the probability epsilon, and otherwise it's uniformly distributed. So with probability epsilon, yi is just xi, and otherwise it has expectation 0. So this is equal to the epsilon to the s times chi s of x. Yeah. Y is with probability epsilon, epsilon times xi. Yeah, so we get. Okay, so intuitively what happens here is that this noise operator, it basically kills the high degrees. We have this power epsilon to the s, which means that it keeps the low degrees alive, the constant degrees, but it essentially kills the high degrees. And we could have instead of applying the noise operator, we could have just truncate brutally and take just the sum of all these f at s chi s where s is small, but then we want to have these nice properties that are preserved. Like when we apply this T epsilon, we get a bounded function, and it's much more convenient that we have a nice operator to do the job for us than just do things brutally. Okay. Also, let's show the first corollary of that. And the corollary is going to be that if we have a low degree polynomial, then we can have a bound on its Q norms. Yeah. So let's start with a polynomial that's homogeneous of degree Z. If we take any Q that is at least 2, we get that, and we get that the Q norm of F is at most Q minus 1 to the D over 2 times the 2 norm of F. the proof here is again very simple. So we take, so we let epsilon be 1 over root q. And then we get that the epsilon of f, the q norm of it, on the one hand, it's equal to epsilon to the d times the q norm of f. On the other hand, it's at most, so it's 1 over square root q minus 1. And on the other hand, it's at most the 2 norm of f. And that's it. Basically, we rearrange, and that completes the proof. And it's true in general that if we have an operator that is hypercontractive, we can look at its eigenfunctions and deduce that they have this property that their q norm is bounded in terms of their 2 norm. Okay. So how to think about these moment bounds? So one example to keep in mind is the function which is the sum of the xi divided by root n. This function, its distribution, it converges to the normal distribution. And if we put the infinity norm, this means that f is always bounded. And for the normal distribution, we don't get that it's bounded, we get that it's almost bounded. The probability that it gets a large value is very, very small. And this is captured by, you can prove it for the normal distribution by computing the q norm of a Gaussian random variable. And so basically, yes, so Chernow's inequality follows from this inequality. And when we take functions of degree 1, and we have a function that we have a similar property for general low degree functions. So this is like one function. Okay, so this you might know because this follows from Chernow, but you can take the function that's the number of triangles in a graph. That's a function of degree 3, and you can prove that it also has these tail bounds, that the probability that it's large, it's very, very small. It's essentially, it's always, its value are always concentrated around its 2 norm. And so there are lots of, I mean, for small p there are these Poissonic behavior, but I mean, just as an example, you can take this function, which is function of degree 3. And so I just mentioned the okay. And so I just wanted to mention that these q norms, if we have a bound on the q norm of a random variable, then we have this Markov inequality that we can apply. So the probability over a random x in the cube that f of x is at least t is the same as the probability fx to the q is at least t to the q. and this is at most the q norm of f to the q divided by t to the q. So this is how upper bounds on q norms translate into upper bounds on the probability that the function takes large values. And for us, we care about Boolean functions. So we'll have a function now that takes values in the set 0, 1. And we would like to say things about its Fourier spectrum. And the main implication of hypercontractivity in that respect is that if we take a Boolean function that takes the value 1 with a very small probability, then all its Fourier mass is concentrated on the high degrees. Okay. So basically, our goal is going to be upper bound the 2 norm of this part. Want to say that this is small. I don't remember if I define that. So this f equal to d part is the sum of s of size d of f at s chi s. Are there any questions?
Solventation W for the norm squared.
Yeah. Yeah, so this thing here is W d of f is the same thing as f equal to d 2 norm squared, which is also the same thing as the sum over s of size d of f at s squared. Okay, yeah, that's a good question. So it's relevant both to the KKL theorem that we talked about. So basically when you want to, okay, so maybe I'll recall some stuff. So so one motivation is from the total influence that we talk about. So we have this ith influence of a function. That's the probability over x in the cube. So we think of f as this voting scheme that we have to choose between -1 and 1, and then the n coordinates are the voters, and the ith influence is the influence of the ith voter. It's the probability that it determined the outcome of the election. And there is the total influence, which is sum of and it turns out that this total influence has this property that it has this nice formula that it's the sum of f at s squared times s. So basically, when we know that all the Fourier mass of the function is on the high degrees, we also get the total influence is large because this s here is larger as s increases. So our goal is to upper bound the low levels in order to show that all the mass is on the high levels, and then we can upper bound the total influence, a lower bound, sorry, the total influence. And we'll also talk about another motivation of small set expansion. Okay, fine. So let's interpret this in a different way. The claim is that if we take the 2 norm of the greedy part of f, this is the maximum over G, whose 2 norm is 1. And G is homogeneous of the greedy. Of the inner product between f and G. So basically this part, it measures the highest possible correlation that f can have with a homogeneous polynomial of the greedy. No. It does. This is for real valued function. For all functions, this is true. Yeah. So maybe let you tell me the proof. So why is this quantity at most distinct? Yeah. So if we take the inner product between f and g, okay, so by definition, okay, so f is the sum over s in n over f at s chi s, and g is only the sum over s of size d of f at s chi s, of g at s chi s. Yeah. So this is the same thing as the inner product between the sum over all s of size d of f at s chi s with g. That follows from Parseval, that tells us that the inner product, I mean, these chi s are an orthonormal basis. So, and now we can apply Cauchy-Schwarz to say that this is at most f equal to the 2 norm times the 2 norm of g, which is 1. Okay, so this is why we have this implication. Why do we have the implication in the other direction? Yeah, okay, so you can take g to be f equal to d divided by the 2 norm of f equal to d, and we get that this is inequality. Okay, so this is basically, so upper bounds on this f equal to d parts are just upper bounds that tell us that if we have a Boolean function, it's not correlated with low degree polynomials. Okay, so if we draw it, we have 2 types of distributions. We have the distribution of a Boolean function. So it's the indicator of some set, where A is a subset of the Boolean cube. And let us write alpha for the density of A. And then we can normalize f to have 2 norm 1. So we'd have to divide by the square root of alpha. And then if we look at the distribution of f, it's going to have this peak here. It's going to take the value square root of 1 over alpha with probability alpha. This is a very peaky distribution. It takes this peak. On the other hand, we have this a smooth distribution of low degree polynomials. So if you take a low degree polynomial, you can think of its distribution as being nice and bounded. So it might take high values, but only with a very small probability. And then this difference in behavior is what makes Boolean functions that with a small alpha, so sparse Boolean functions, uncorrelated with the low degree polynomials. Okay, so okay, so we'll soon see how hypercontractivity gives us this uncorrelation between Boolean functions and low degree polynomials, but let's start with the trivial things. So if we have, so first, what is the trivial upper bound? So we can always say that the two norm of f equal to d. This is at most the two norm of f, which is square root of alpha, because f only takes the values 0 and 1. So this is like the trivial bound. And let's say that we have a function g. So let's say y into upper bound g, and we know the g is bounded. So suppose that g is a function that takes value in the interval minus mm. It only takes, yeah, let's think of m as 1 or something. So g is a bounded function. Then we can say that the inner product between f and g, this is at most the L infinity norm of g times the L1 norm of f. So the expectation of fg is at most m times the 1 norm of f. So this is going to be alpha times m. So when alpha is small, we get something that's much smaller than this root alpha. And upper bounds on the Q norm, they let us to get some inequality in between this alpha and this root alpha. So that's going to be our first application called the level D inequality. Okay. I guess it's reasonable to attribute it to KKL or to BKS. So Tukan Kalai lineal and Benjamini Kalai Shram. And what? Okay, so it tells us that if we have a function f from the Boolean cube, 0, 1, and the expectation of f is alpha, then the two norm of f of the low degree, the degree d part of f, this is at most alpha squared. So roughly what you get from this example, but then you'd have to pay some logarithmic factors. So you have like 4 of 1 over alpha divided by d to the d. Okay, and we need d to be at most log 1 over alpha divided by 8. So roughly alpha squared, and then we have these extra polylogarithmic factors, at least when d is constant, and the statement is effective up to log 1 over alpha. And that's sort of why in KKL, the theorem goes up to log n.
So is it still the case where f is an indicator? Is it still the case where f is an indicator?
So f is the 0, 1, so it's indicator of
0, 1.
Yeah, this theorem is definitely not true for general functions because f could be a function of homogeneous polynomial of degree d. So, but you can actually formulate some theorems for general functions that instead of alpha, you can put here the 1 norm of f. Instead of log 1 over alpha, you can put the 2 norm of f divided by its 1 norm. Okay, so let's move it. So the idea is to we take this 2 norm squared. This is the inner product between f equal to d. Does anyone have an idea what should we do now? Earlier we had Cauchy-Schwarz that we put here 2 and 2, and then it gave us nothing. Here we put infinity and 1. So what can we do now in order to get use hypercontractivity to get something? Yeah. So we can use Hölder's inequality exactly. So we can upper bound the low degree part, it's Q norm and F. We can bound, and we can put the Q prime norm where 1 over Q plus 1 over Q prime is 1. This is Hölder's inequality. And okay, then we have to choose Q. But let's first, okay, so now we can upper bound this part using hypercontractivity. So this is at most square root Q to the D times the 2 norm of F. And this part, this is the expectation of F, the power 1 minus 1 over Q. Now both of them. Okay. And we would sort of like to get rid of this expectation of F to the 1 over Q. And
So D is, I just can't read it. D is log 1 over.
did I choose D?
You don't.
D is at most something, yeah. It's some upper bound on. Yeah. Yeah. Okay. Yeah, so we would now like to get rid of this expectation F to the 1 over Q and get this alpha square dependence to get here the expectation of F. So basically we choose Q to be log 1 over the expectation of F divided by D. And then we get that the expectation of F 1 over Q minus 1 over Q, this is just 2 to the D if we take this log in base 2. And we're already losing a squared Q to the D factor, so we don't mind losing this extra 2 to the D factor. So we get that this is at most, what we had over there is at most 2 square root Q to the D times norm of F equal to D times the expectation of F, which is alpha. So now we can just rearrange and we get that norm of F equal to D squared is at most alpha squared times 4 log 1 over alpha over D. And it turns out that this theorem for d equal to 1, this is equivalent to Chernow's inequality. And you basically get some version of Chernow for low degree polynomial. Are there any? Yeah. This 4 is definitely not tight, but other than that, yeah.
No, in the sense that like
Yeah. So other than the constant to the d, this is sharp. Yeah. Yeah. You can take a hummingbird, and it's going to be sharp for the hummingbird. So we got that most of the mass of a Boolean function is concentrated on the high degrees. And yeah, and okay, and another consequence that we can get of that is the small set expansion theorem. And this is about a property of this noisy process. So tells us the following. Which epsilon there exists delta. Such that if we have a small set, so such that if we have a set of density at most delta, then we are going, if we take a random step of the random walk, we are going to leave the set with high probability. If we choose randomly a random element of A, and then we choose a random element according to this noisy random walk, let's say n1/2 of x, which coordinate we remember it with probability 1/2 and forget it with probability 1/2 and resample. Then when we do that, we can no longer guarantee that y is in A. So we're going to leave A with a high probability. So there isn't like this set that forces you to stay inside. Every small set you're going to leave. Probability that y is in A is going to be at most epsilon. And this you can also think of geometrically. It means that if you take, so if you look at the cube, and you have a small set A, then most of the elements in A are near the boundary. It's like a high dimensional phenomenon that if you take a ball, most of the elements, if you take a random element, it's going to be near the boundary, and it's going to get out of the set with high probability when you take this random step. Okay, so let's prove it.
Just gonna ask what steps.
Okay, so we have this operator E1/2 F inner product with F. This is a Fourier interpretation, but it also has this probabilistic interpretation. So this is the expectation over X in the cube of T half F of X f of x.
So f is the indicator of A now?
Yes, so and then this is the expectation over y, f of y, f of x. So this is just the expectation over x and y, and we get that this is the basically the probability expectation over x uniformly distributed over A. So, okay, so we have this expectation over f of x. We can get rid of that. So first we need x to be in A. So this happens with probability alpha. And after we know that x is in A, we have to take this probability, that this y is in A. It's in A. And what we want, and what we want to show that, yeah, so basically our goal, we want to show that this part is little o of 1. This, yeah, so the goal is to upper bound. Different, okay, yeah, sure. The goal is to show that the probability that y is in A, that this is at most epsilon. So we want to show that, yeah, so alternatively, this is to show that the inner products is at most epsilon times alpha, which is epsilon times the 2 norm of f squared. Don't learn from my mistakes. Now, how do we upper bound this thing? We can just use the Fourier expansion. So you have f inner product with f. This is the sum over s of half to the s times f at s squared. And this is equal to the sum over d from 0 up to n of half to the d times the 2 norm of the degree d part of f. And now we can, and then we can divide it into two sums. So we have the sum over d, which is at least log 1 over epsilon, log 2 over epsilon, of half to the d. It's going to be epsilon because I want to show the probability is at most epsilon. Yeah. So this is at most, yeah, so this is this thing plus the same thing with the smaller than log 2 over epsilon. So here we're going to upper bound this by, this is at most, this half to the d becomes epsilon over 2. And the sum of all of these 2 norms, this is at most the 2 norm of f. And for the low degree part, we have this inequality. So we can upper bound it by sum from d equal to 0 up to log 2 over epsilon of alpha squared log 1 over alpha divided by d times 4 to the d. And we have maybe another extra half to the d. But the point here is that here we have alpha squared and it beats all the other factors. This is most epsilon alpha, provided the delta is sufficiently small.
Where does delta get used?
Yeah, so alpha is smaller than delta, so that's why, yeah.
Can you get the isoperimetric inequality? That's even something.
Which inequality?
Isoperimetric.
Yes, the isoperimetric inequality, yeah, you also get it. The isoperimetric inequality tells you that for each d up to log 1 over alpha, the mass at this level is negligible. So all the mass is up above level log 1 over alpha. Then you get the isoperimetric inequality. Yeah, that's true. Yeah. I actually plan to sketch that. So that's okay. So other corollaries. Okay, so one of them is the isoperimetric inequality, which has the same proof. So the edge isoperimetric inequality, yeah, it tells us that the total influence of f is at least some constant times alpha log 1 over alpha, where alpha is the size of a over 2 to the n. Let's say that this is at most half. Yeah. So we have a small set, then total influence of it is at least C alpha times log 1 over alpha. So if you want to prove that, the same proof works. Basically, you have this upper bound. So let's just proof sketch. So all d smaller than log 1 over alpha divided by 8. And this weight at level d is negligible. You get that the sum over d at least log 1 over alpha to the 8. This is at least the 2 norm of f over 2. Is alpha over 2. So all of the mass of most of the mass of the function is above the level log 1 over alpha. As mentioned, the total influence of f is the sum of s times f at s squared. So we get that this is at least log 1 over alpha over 16 times alpha. So we get that this mass here is at least alpha over 2, and it's multiplied by this s, which is always going to be at least log 1 over alpha. Okay, so that's for the isoperimetric inequality. You have the KKL theorem, which is slightly more tricky. That's the Kankali lineal theorem. It says that if basically, say if all the influences of f smaller than delta, then the total influence of f is at least 2 to the minus O of 1 over delta, and this is sufficient to imply this other version of the KKL theorem that tells you that the maximal influence is at least log n over n. Okay, so basically it says that if the influence is so small, the total influence is large. Okay, so here we had a small set. We assume that we have this small set, and we got in the isoperimetric inequality this factor of log 1 over alpha. In the KKL theorem, we don't have a small set. The KKL theorem is for an arbitrary function. It could take expectation 1/2, could contain half of the element, but then the idea is to use the fact that the derivatives of the functions, they are small sets. So if we take the set of x such that f of x is different than f different when we change the I-coordinate, this set is a small set, and therefore this set contains all its mass on the high degrees. Yeah, that's sorry. Yeah, it should be log 1. The other way.
It was less than 1.
Thanks. Yeah. So we have these derivatives, and this is called like DIF. Okay, now maybe sign. Okay, so you can let DIF be f of x minus f of x when you change the i's coordinate, and this as the Fourier expression, the sum over all s that contain I of f at s and sky of s minus I. So this is the discrete derivative, but it's also the derivative of f as a polynomial. 2 minutes, okay. And then this is a small set, or at least this thing is a small set. So we get that most of the mass of the derivative is on the high degrees. And then once you know that all the mass of all the derivatives is on the high degrees, you can get that also the mass of f is on the high degrees. And this is what makes its total influence large. Okay. So I think I'll stop here.
Any questions?
Hyper-contractivity being this sort of powerful tool, can you show that the noise operator is hypercontractive? I'm curious, how much do we know about like other operators in hypercontractivity, like for example, like Cayley graphs? Like, how do you know if I give you a set of generators for a Cayley graph? Can you tell me whether or not that matrix will be hypercontractive or not? Does that make sense?
Yeah, that's a good question. So, so hopefully at some point in this semester we'll talk about hypercontractivity on other settings. So you can ask for hypercontractivity in the symmetry group or the bilinear or Rotter-Grassmann, and basically what we did here is we had this operator that was hypercontractive, and we deduced some bound on its eigenfunctions, and we had this approach for Sn, where instead of like constructing for showing for specific operators that they are hypercontractive, we managed and we constructed some operator that's hypercontractive, but it was sufficient to imply that its eigenfunctions have this nice properties. And basically, if you talk about Cayley graphs, so if they are normal Cayley graphs, at least, which means that the generating set is closed under conjugations, the eigenfunctions always look the same. It's the same eigenfunctions. So once you find any normal Kelly graph that's hypercontractive, you essentially got these nice properties for all the Kelly graphs that you care about. And
Any more questions?
Start with the answer. So there's another silly example where you change exactly if you change exactly at the end of the coordinates, that's also hypercontractive. That's a silly example, but the real thing, if you look at the random walk, then the spectral gap corresponds to something known the Poincare inequality. And then the hypercontractivity corresponds to something called the log subwave inequality, which is known to be stronger. So it implies a spectral gap, but it's strictly stronger. And there's something in the middle called modified log subwave inequality, which is equivalent to something called reverse hypercontractivity, which is like hypercontractivity, but for norms less than 2.
They're not equivalent.
Okay, so maybe they're not equivalent.
Let's take it offline. So let's take Noam again. So now